Hi, I'm Keenan Crane from Carnegie Mellon University, and I'm going to talk about how we can solve equations on extremely complicated geometry using Monte Carlo methods. So, just like Monte Carlo revolutionized photorealistic rendering around the 1990s, the Monte Carlo methods I'll discuss in this talk provide some very powerful tools for broader problems in science and engineering. This work started with my PhD student Rohan Sahani, and more recently with a growing list of collaborators from CMU and Dartmouth and elsewhere. A basic motivating problem is the classic interpolation problem. You have some region, omega, with known values along the boundary, and want to smoothly interpolate these values into the interior. This is what's known as the classic Laplace equation, Laplace u equals 0 on omega, subject to Dirichlet boundary conditions u equals g on the boundary of omega. Now, many of us have been trained, including myself, to think about solving this kind of problem using finite dimensional approximation. For instance, build a mesh of the domain which can be used to define basis functions, phi sub I, then compute a solution, a function u, that satisfies our Laplace equation in a weak sense. Of course, if you do this, you necessarily have error due to approximation of the geometry and also due to approximation of the underlying function space. But there is another way. We can actually avoid finite dimensional approximation completely by using Monte Carlo. For the Laplace equation, this starts with something called Kakutani's principle, which says that if I want the solution at a point x, I can just take a bunch of random walks to the boundary, grab the boundary value g, and then take the average or expected value of those boundary values. There's only one problem, which is, well, how do I simulate a random walk? It feels like I still have to take little finite time steps. Actually, what I can observe is that a random walk starting at a point x is equally likely to exit through all points on a sphere around x. So if I just uniformly sample the sphere, then I haven't made any statistical error at all. And this is the starting point for the so-called walk-on spheres algorithm, which says that to solve a Laplace equation at x naught, I take the biggest empty sphere around x naught, uniformly sample that sphere, and repeat until I reach the boundary. Of course, this is like Zeno's paradox of motion. I never actually reach the boundary. But when I get within some epsilon neighborhood of the boundary, it's probably fine to just go ahead and grab the closest boundary value. A completely different way to motivate this same algorithm is through the mean value property of harmonic functions. Namely, the value at any point, xk, is equal to the average value over any sphere around that point. And so if I repeatedly estimate this mean value integral using a single random sample, then I'll again get this same walk-on spheres algorithm. And this sort of duality between the stochastic point of view and the integral or potential theory point of view will become important later on. But before getting too excited about this strange and different approach, I might want to ask, well, why? Why would we want to do it this way rather than just build a mesh like we always do? And I hope you'll excuse me for a moment if I indulge in some propaganda about Monte Carlo methods and why I think they're interesting. And the basic reason for seeking out alternative strategies is, well, geometry is hard. Even really smart people at Pixar are saying they hate meshes. They cannot believe how hard this is. And in contrast to meshing, finding the closest point on the boundary of a domain, like we need to do for walk-on spheres, is a relatively simple operation. This is super important because geometry is only getting more and more complex as the years go on. We have extremely detailed data coming from laser scanning and shape optimization and computer vision. And even after decades of working on methods for solving PDEs, we still struggle to handle the level of geometric complexity that we encounter in nature. In fact, even state-of-the-art tools can take literally hours to mesh a single model. And so even if your finite element solver is super fast, it doesn't matter because you're spending all your time converting your domain into a mesh that's good enough for simulation. This is especially tough because geometry encountered in the wild can be really bad. To quote Jean-Paul Sartre, hell is other people's meshes. And if you've worked with real data, you know he's right. Now, one approach is to just keep pushing on better and better meshing tools. And to be fair, these have gotten extremely good, especially in recent years. But meshing really feels like a problem that will never be completely solved. Even with the latest and greatest tools, you run into situations where geometry can take hours to mesh, and even when the algorithm terminates, it might not give you what you want. It might miss small details that completely change the meaning of the solution. So back in the 1990s, people ran up against the same kinds of problems with rendering. If you wanted to make a photorealistic image, you would probably use something called finite element radiosity, where you make a mesh of the scene, you build a large linear system, and then solve for the illumination everywhere in the scene. And this idea fell out of fashion for many reasons, but in large part because meshing is, again, just really, really hard and painful. Instead, the rendering community moved away from finite element methods and toward Monte Carlo methods where you recursively shoot rays that bounce around the scene. And so now instead of meshing, you just have to compute where a ray pierces the domain boundary, which is way easier to do. Beyond just being a beautiful idea, the shift to Monte Carlo methods really enabled modern photorealistic rendering and has had a major impact on industries like entertainment and industrial design, and these days, computer vision, where we're seeing leaps and bounds in the ability to reconstruct 3D objects from photographs. Of course, there are a lot of physical problems beyond light transport which show up in lots of important applications. And so this is where, I believe, Monte Carlo methods can provide a lot of the same benefits for science and engineering. For instance, just as in rendering, as long as the problem we want to solve is well posed, we can be confident that Monte Carlo methods will produce a physically meaningful solution. We don't have to know, for instance, which function space we're working in or find finite elements that span that space or anything like that. Just like rendering, the cost of adding geometric detail grows like n log n, which means we can easily scale to problems with literally billions of elements. So here's one PDE on the right that we solved where the boundary mesh has over a billion elements. Just like rendering, you get perfect parallel scaling by just averaging the results from n different processors. Just like rendering, you can immediately get a reliable preview of the solution by taking just a few samples. So here I'm showing a PDE being solved in real time in a shader program with no pre-computation. Just like rendering, you can work directly with a mix of different geometric representations like meshes and implicit surfaces without having to generate a separate finite element mesh. Just like rendering, you get a totally reasonable solution even if your geometry has major defects like cracks and self-intersections. Just like rendering, where you shoot out rays only for the pixels that you want to see, this walk-on spheres algorithm lets you evaluate the solution only at the points where you actually need it. And you're not forced to use Monte Carlo everywhere unless you really want to. In rendering, for instance, we're now seeing a lot of use of ray tracing inside rasterization pipelines. In principle, you could also use Monte Carlo methods somewhere inside an existing mesh-based simulation. Now, despite my exuberance about this approach, I'm not naive. There is amazing work on solving all sorts of physical equations that we may never be able to do using Monte Carlo methods. But at the same time, given how far Monte Carlo has brought us in helping to understand and simulate and predict illumination, we would be absolutely crazy not to see what we can also do for science and engineering. Okay, enough with the propaganda. Let's get back to looking how we can actually estimate the solution to various equations. These ideas, by the way, have been around for a while, but have been kind of forgotten in time. The earliest record I know of are some brief remarks in a book on numerical methods. Then in 1956, Muller really lays the groundwork for walk-on spheres, and he understood the propaganda even then. He says, as long as the problem is well posed, you don't have to worry about the geometry. As with any good algorithm, this one was reinvented a decade later under the name floating random walk. Then much later, Binder and Braverman gave a thorough analysis of its performance and complexity. And over the years, there have been maybe a couple dozen papers that propose various extensions, but compare that to finite element methods, which probably have tens of thousands of papers written in the same period of time. There have also been some applications of walk-on spheres, especially to integrated circuit design and a few other things, but that's really about it. And the main reason why this hasn't been taken further is that so far, walk-on spheres applies to a very limited class of partial differential equations. So that's really our mission, or our call to action has been to try to expand the kinds of problems and hence the kind of applications that can be solved using these Monte Carlo methods. So let's begin by looking at some basic facts about Monte Carlo. The idea is I have an integrable function f, and I'd like to compute its integral I over the domain omega. To do that, I'm going to take n uniform, independent random samples, evaluate the integrand at these points, add them up, divide by n, and multiply by the volume of the domain. One very important fact about this estimator is that it's always consistent, meaning that as I keep taking more and more and more samples, it will converge to the true integral with no further hypotheses on the function f. So nothing about its regularity or anything like that. So it's a very general technique. Fact 2 is that the estimate is unbiased, meaning that the expected value of the estimator is equal to the true value of the integral, or more intuitively, I get the exact solution on average, even if I take only one sample, and we'll use this fact a lot. Fact 3 is that the error is very predictable. For any function in any dimension, the error goes like 1 over the square root of the number of samples. Another basic tool we'll need are closest point queries, which for a given query point x, find the closest point x prime on the domain boundary. So for instance, if our boundary is just a single line segment, then we can easily write down a little explicit formula for x prime. And the distance between these 2 points then gives us the sphere radius for walk-on spheres. So the details of this formula aren't particularly important. A more important observation is that these atomic queries are easily combined to get the closest point on a more complicated set. For instance, if our boundary is now 2 line segments, A and B, then we can just take a minimum of the individual distances to get the distance to the closest point on either A or B. And for domains made of many small pieces, let's say many line segments, we can also accelerate these queries using a standard spatial data structure like a bounding volume hierarchy, which lets us compute the closest point to n objects in only log n time. So given those basic components, how do we come up with a walk-on spheres estimator for a given differential equation? The path I'll take is to first find a stochastic representation for the PDE over a general domain, then convert it to a deterministic integral representation over a ball-shaped subdomain, which can then be estimated via Monte Carlo. One kind of funny thing is that in retrospect, you can often give the whole derivation without the stochastic picture. But the reality is the stochastic approach is pretty important for developing a lot of the ideas in this area, and it would be pretty hard to get by on just the integral picture alone. I'll also mention that in this section of the talk, I'm just going to give estimators that are correct. So later on, I will talk about how to make these estimators more efficient. So here's the PDE that I'll consider today. And if we imagine the solution U represents, for instance, the temperature of the domain, then the boundary values G describe fixed temperatures along the boundary. A source term F describes kind of the background temperature. A term sigma U, an absorption term, describes sort of cooling due to absorption of heat into the background medium. A drift term, omega dot grad U, sort of models heat getting dragged along with a flow of velocity omega, and the scalar function alpha in the second order term describes how quickly heat diffuses through the domain. Now, in general, these coefficients could vary over space, but for simplicity for the moment, we're going to assume that these coefficients are constant. Okay, so with all our basic concepts in place, let's actually write down a walk-on spheres estimator for each term of our PDE. We will start with what we already saw at the beginning, a Laplace equation with Dirichlet boundary conditions G. And to handle this boundary term, we had Kakutani's principle, which says that we're going to take a bunch of Brownian random walks to the boundary and take the expected or average boundary value. To actually simulate this process, we restricted our attention to a ball around the point X and replaced the boundary values G with the unknown values U of our harmonic function. So in this case, the expectation just becomes our usual mean value integral. Now that we have this deterministic integral, we can estimate it using Monte Carlo. So uniformly sample points on the boundary of the ball. Those are our points y sub I. And recursively evaluate our estimator for u. As mentioned before, this estimator and any Monte Carlo estimator will remain unbiased even if we take only a single sample so setting n equals 1. And so then to estimate our boundary term, we simply recursively sample a point on the largest ball around the current point. And we get an algorithm that looks like this. It started at x0, sample x1, sample x2, and so on and so forth. And as we said before, for this to ever terminate, we need to then jump finally to some point on the boundary, the closest point on the boundary, which is going to introduce a small but controlled amount of bias. Our entire solver for the Laplace equation boils down to about 10 lines of code. So initial our estimate to 0, then for some number of walks, we start at the evaluation point x0, we find the radius of the largest empty sphere around this point, and sample a new point until we come within epsilon of the boundary. We then add the closest boundary value to our estimate, and in the end, we return the average of all the boundary values we've seen along the way. Okay, but we already saw all that at the beginning, so how do we add new terms like a source term? So here, the stochastic picture is basically that as our walker wanders around the domain over the total time t that it takes to reach the boundary, it's going to feel and pick up this background radiation f. Okay? So then the question becomes, how do we account for this additional heat in our Monte Carlo estimator? Well, we can again just think about one of our balls and ask, where does the particle spend time while wandering around inside this ball? So you can imagine a bunch of random walkers that sort of leave trails of where they go. And if we average this picture over a very long time, what we get is something that eventually looks like the harmonic Green's function for a ball, which we know in closed form. So we expect to pick up background radiation equal to the integral of the source term f times the Green's function g over the ball. Once again, we can approximate this integral using a one-point Monte Carlo estimator, which means we sample a point uniformly from inside the ball rather than on the ball boundary, and evaluate the source term and Green's function at this sampled point, and multiply by the volume of the ball. Our overall estimator is then the same as before, except that we now add this additional contribution at each step, right? So instead of just sampling the next point x sub k, we also sample a point y sub k inside the ball at each point, and then finally jump to the boundary. Likewise, our code gets longer by just a few simple lines. How about absorption? Well, the idea now is that the longer a particle wanders around our domain, the more likely it is to get killed. So we have a cumulative probability described by exponential decay. To turn this into a deterministic integral, we can ask where the particle spends time inside the ball, just like we did before. And now we get a different Green's function, sometimes called the Yukawa potential, that depends on the absorption parameter sigma. We also need to know how likely it is that the walker reaches each point on the boundary of the domain, or the boundary of the ball, which we can do by tabulating the exit distribution, or what's called the Poisson kernel, associated with this stochastic process. Okay? So the overall expression for the solution u is then the integral over the ball of the source term times the Green's function, plus the integral over the ball boundary of the unknown function u times the Poisson kernel p. So this is what you would see from just ordinary potential theory. To incorporate drift, as you might have in a convection diffusion equation, we now transition from a purely Brownian process to a diffusion process with drift, and everything kind of works the same way. This time the Poisson kernel is given by what's known as the von Mises-Fischer distribution, which also shows up in volume rendering and is related to the Green's function by a normal derivative. Okay, and this is our general recipe. If we know the Green's function and the Poisson kernel, then we know how to apply the walk-on spheres algorithm. Okay, so that completes the sketch of how we go from our second-order PDE all the way to a Monte Carlo estimator. A small but very useful observation is that we can also compose differential operators by nesting estimators. For instance, if I want to solve a fourth-order biharmonic equation, Laplace squared u equals f, I can write this as two second-order Poisson equations, delta u equals v and delta v equals f. And then every time my estimator needs to evaluate v, I can just think about that as estimating a source term, and instead of sampling a single point, I'll take a whole walk on spheres all the way to the boundary, like this, okay? So there's a kind of obvious problem here, which is that this is horribly inefficient, since if n is the maximum number of steps in any walk, I now have to take order n squared steps rather than just order n. So I'll describe a way to speed that up later on. Another very nice thing I can do with walk-on spheres is estimate spatial derivatives of the solution. So if we again have our basic Laplace equation, we know the value at a point x is represented by our mean value integral, and the gradient can be expressed with something that looks almost the same, except that we take the average value times the normal of the bounding sphere. This is basically an application of Reynolds transport theorem. If we wanted to take a directional derivative along z, we would shift the ball a little in the z direction and pick up a contribution proportional to z dot n. And once we can estimate the gradient or the directional derivative, we can also estimate any other first-order operator like curl and divergence and so forth. Finally, we can estimate higher-order derivatives like the Hessian of the solution, which in our case we did using some tools from stochastic calculus. And from there, we can also estimate any second-order derivative of the solution pointwise. Now, it may be worth mentioning this is something you can't necessarily do with finite element methods because you may only know the solution up to some number of derivatives. Now, real systems, of course, can exhibit some very complex spatial variation, maybe capturing fine-scale structure and material properties. And so we'd really like to be able to solve PDEs where the coefficient functions continuously vary over space. So I won't go through all the details here, but the basic strategy is to transform this variable coefficient PDE into one where all the variability is captured by the source term. So the sketch of this process is that we start out with our general second-order equation. To push all the variability from the second-order term into the first-order term, we basically just apply the product rule and divide by alpha. Then to push the variability from the first-order term into the zeroth-order term, we apply a Gersonov transform, which is basically a change of measure for our stochastic process. Finally, to move the variability from the zeroth-order term into the source term, we use a technique called delta tracking, which actually comes from volumetric rendering. Okay, and then we get a constant coefficient, PDE, that we can estimate using the estimators that we've already described. What we get in the end, in particular, is this Screen-Poisson equation where I've made all sorts of variable substitutions, okay, but don't worry about these. The main point is that we now have this kind of funny-looking PDE where the solution u appears on both sides of the equation. And from a finite element perspective, we really didn't make life any easier, right? To solve this, we would basically have to move all those terms back to the left-hand side to form the stiffness matrix. But for Monte Carlo, solving recursive equations is no problem at all. For instance, we always have to recursively sample our solution to evaluate our boundary term. Now we just have to also estimate it for the source term. And so our overall estimator looks like this. To evaluate the solution at a point x sub k, we estimate the boundary term at a point x k plus 1 sampled from the sphere, and we estimate the source term at a point y sub k sampled inside the ball. Now, if we do this naively, we have a problem because the number of samples we need is growing exponentially. We have 2 new samples for each sample. So what we can do instead is just flip a biased coin. Sometimes we sample the boundary term, sometimes we sample the source term, and then we just weight these 2 terms appropriately. The real takeaway here is that walk-on spheres is not just another way to think about integral formulations, which are already widely used, for instance, in boundary element methods. But rather, it lets us pull off kind of fundamentally different tricks and transformations that can only be solved by recursively approximating integrals. And this viewpoint of recursive integral equations is also what lets us to connect to a deep knowledge from rendering. The rendering equation is a recursive integral equation. In fact, if you write out the volumetric rendering equation for the radiance L in something like a cloud or a puff of smoke, then what you see is that structurally it's almost identical to the Feynman-Koch formula for our PDE. So we'll exploit this connection a lot as we continue. Especially because there's a lot of deep knowledge from rendering and computer graphics about how to accelerate these kinds of calculations. So far we have estimators that are correct, and now we would like to make them more efficient. For Monte Carlo, efficiency means, well, we'd like to either reduce the cost of evaluating the estimator or decrease the variance of the estimator, where variance is basically how much our estimator deviates from the true integral on average. If you recall, the variance for all Monte Carlo methods is inversely proportional to the number of samples, but as we've seen in rendering, the constants in these estimators can make an enormous difference in practice. One classic technique for reducing the variance of an estimator is importance sampling. So if I have some complicated integrand f of x, it really doesn't help much at all to put samples where f is small, right? I'm not adding much to my estimate. But if I have a decent approximation of my integrand that I can easily draw samples from, then I can weight my estimate so that more samples are placed in larger regions. And then I just weight those samples accordingly. What does that mean for PDEs? How do I importance sample a partial differential equation? Well, if we consider the source contribution, one thing we might do is use the Green's function g to do importance sampling, since this distribution is often known in closed form. So here we have to be a little bit careful since g is singular, but if we do our importance sampling in polar coordinates, then the singularity essentially goes away because we now have g times the area measure. So in 2D, g times r. So now rather than picking a point uniformly from the ball, what we're going to do is sample uniformly in the range 0 to 2 pi, then sample the radius from this distribution rg, and finally evaluate the source term f at this new point, y equals r theta, divide by the probability p that we sampled from this distribution. Alternatively, we can importance sample the source term in this integral. So suppose that inside my ball, I have a point source z, like a little pinprick of heat. I have a source concentrated onto a curve gamma, kind of like a hot wire, and a source supported on some two-dimensional region or n-dimensional region. If I don't do any importance sampling, then I'll get something like this. I'll miss these point and curve sources because they get sampled with probability 0. But if I use a proper importance sampling strategy, then these will show up as we might expect. In particular, for a point source, my importance density is going to be what you might think, just a Dirac delta centered at the point z, which means my importance sampling strategy is, well, I just grab the value at z and multiply by the Green's function. To importance sample a curve, I'm going to take uniform random samples from the intersection of that curve with the ball, and then evaluate the source function and the Green's function at those points, multiplied by the length of the restriction of the curve to the ball. Okay. A very natural question to ask is, well, I have these two different importance sampling strategies. Which one should I use? For instance, in rendering, I have a similar choice to either sample the lights or sample the materials, and different strategies are going to work better in different scenarios. But there's a very nice observation from Veach and Guy-Boss that says, well, we can actually always combine different importance sampling strategies in a way that's provably never much worse than optimal. And this really helps to improve the robustness of these Monte Carlo estimators. So we can now do the same thing for walk-on spheres for these PDEs and say, well, if we have, let's say, a screen Poisson equation where the absorption parameter sigma is kind of going to affect which strategy is better, we can automatically get the best of both worlds by using this multiple importance sampling. Another way to increase efficiency in rendering is to reuse parts of paths that have already been computed. And this actually doesn't decrease the variance of the estimator because the paths are now more strongly correlated, but it can significantly increase efficiency because paths are expensive to generate. Likewise, let's consider our biharmonic equation, Laplace squared u equals 0, which we split into a system of two second-order equations, Laplace u equals v and Laplace v equals 0. And so now, instead of taking a completely new walk for each source point y, which has quadratic cost, what we're going to do is let y walk back to the boundary along the same path as x. So overall, we just have a linear cost. Again, we're going to reuse all that hard work we already did finding walks to the boundary. This scheme really pays off, as one might hope, even though, again, correlated walks have higher variance. They are much faster to compute, and so we have an overall improvement in efficiency here, about 150 times faster for similar amount of error. Finally, for variable coefficient problems, we can adapt techniques from volume rendering. For instance, a technique called delta tracking kind of fills up a heterogeneous volume with fictitious matter that makes the problem computationally equivalent to a uniform density medium, essentially what we did when transforming our PDE into one with constant coefficients. The next flight method is very similar in spirit to our tree walking strategy, allowing one to reuse paths in the context of heterogeneous media. And weight windows make sure that all paths have roughly equal weight by either splitting high weight paths into multiple independent paths or killing low weight paths with Russian roulette, again, increasing efficiency. So we've done some work to adapt all of these schemes to something appropriate for walk-on spheres, and in practice we get the same kinds of improvements in efficiency as people do for volume rendering. Another sort of orthogonal approach to improving efficiency is denoising. So right now, denoising Monte Carlo renderers is kind of a hot topic in real-time rendering, and you can get some pretty amazing results from even just one or a few Monte Carlo samples. Actually, it turns out many of these denoising methods can be used off the shelf for walk-on spheres. For instance, we applied Intel's Open Image Denoiser to our walk-on spheres estimates and can easily get beautiful results with just a few samples. And this is really just the tip of the iceberg, because we have this nice bridge between worlds now. There are decades of strategies from areas like rendering and stochastic control and mathematical finance that can be used to help solve partial differential equations, though it does take a little bit of thought in each case to translate from one domain into the other. Of course, it's important that we're really getting the right answer here and not just making pretty pictures. So a few words about validation and comparison to other methods. A very basic question you might have is, well, when does walk-on spheres work and what kinds of solutions does it produce? So let's look at our basic Laplace equation again. And a really nice thing about walk-on spheres is that, well, as long as this problem is well posed, we're going to get the right answer. So the only thing we have to assume about the problem is that a solution exists in the smooth setting. For this Laplace equation or this Dirichlet problem, what that means is we just need the boundary to be sufficiently regular, and actually the boundary data doesn't even need to be continuous. That is in and of itself interesting because it means the solution we get might not be in H1. And in particular, that means we're talking about a much larger space of solutions than we ordinarily do with finite element methods. We can also talk about properties of the algorithm. So Muller, for instance, proved the very basic fact that walk-on spheres reaches the boundary with probability 1, and most importantly is he showed that the exit distribution of this walk-on spheres procedure is the true harmonic measure on the boundary. So that is why it's giving us the true solution to the original PDE. Another useful fact is that the spheres don't even need to be the maximal radius spheres. The spheres just have to be bounded away from 0 in order to get this convergence. And you can find similar results for other differential equations. In terms of the computational complexity, Binder and Braverman did a very thorough analysis of this algorithm, showing that it takes order 1 over log epsilon squares steps to reach the boundary in 3D, or if we're in 2D, or if the boundary is smooth, only 1 over log epsilon steps. Okay, so really converges quite fast. And to kind of see what that means, let's take a look at a little example where we're going to start out and make the epsilon shell huge, right? So we're going to say, basically, as soon as you start, you just jump to the boundary and grab the boundary value. And what we get is something that looks a little bit like a Voronoi diagram of the boundary conditions. As we start decreasing epsilon, so waiting longer and longer to jump to the boundary, we very quickly get something that looks like the right solution. And we see that the number of steps per walk is increasing very slowly. And so we don't really need to worry too much about tuning this parameter carefully. We can verify empirically that our estimators converge at the expected rate, not only the estimator for the solution, but also for the derivatives. And then comes a question that people always ask me, okay, so this is all well and good, but at the end of the day, which one should I use? Should I use walk-on spheres or finite elements? Which one is better? And to me, when I hear this question, I always think, well, this kind of feels like comparing apples to oranges. Like in particular, what do you want me to measure to tell you which one is better? So in finite element methods, usually the way that you talk about error is in terms of the order of accuracy. You might say if I have a node spacing h, then the error goes like h to the k. Well, this question of order of accuracy really isn't meaningful for walk-on spheres. There's no such thing as node spacing, and we just have the usual order 1 over n variance, or 1 over root n error for n walks. And in fact, even Muller kind of comments on this. He says, well, the only inherent possible source of error with these processes results from the statistical fluctuation of the estimators. And so the answer I would first give is to say, well, generally, these are very different methods. They have very different capabilities. They have very different use cases. And the best thing to think about first is, what is the appropriate problem for each of these methods, not which one has, the faster rate of convergence. Now, when I say that, people say, okay, but that still sounds like a cop-out. Just show me a comparison, right? Tell me something. And so fine, here's a comparison. I've gone ahead and I've measured all sorts of statistics about doing a solve with finite element methods or Monte Carlo, and you can look at different things. Like when we meshed the problem with finite elements, well, the mesher couldn't handle all the details, so it simplified it to 2 million triangles. The Monte Carlo solver, when we ran it, we had fewer pixels than we had nodes in the FEM mesh. The pre-computation time for FEM was about 14 hours. For Monte Carlo, it was 0.4 seconds. For finite element methods, it took 13 seconds to do a solve. For Monte Carlo, it took about 57 seconds. In the end, you look at these numbers and you could say, okay, well, I don't know who won. Which method is better? I don't know. I don't have a great answer to that question. Although one number that really jumps out at me is certainly this 14 hours of pre-computation time from building the mesh, right? And then also all these other problems that we've talked about before, like loss of geometric detail when you use a finite dimensional approximation of your problem. Now, to that, sometimes people say, hey, that's no problem because there are these methods in the finite element world that guarantee that you capture all the detail you need, in particular something called adaptive mesh refinement. So let's go back to this problem where we have these billions of boundary elements that I mentioned near the beginning, and run adaptive mesh refinement on just one of the many objects in this environment. Okay, and if we do this using just ordinary meshing that's not adaptive, well, we're not going to resolve all the detail in the solution. So it's not just a question of did we resolve the geometry, but also did we resolve all the features in the solution itself. If we go ahead and use this adaptive finite element meshing, then we do capture all the geometric detail, all the detail in the solution. But what you notice now is this gives us 8.5 million tetrahedra. It takes 2.5 hours. And that's just for one object in this problem, right? Forget about solving this kind of infinite array of blackbody emitters. So the next thing people sometimes say is, hey, you're having all this difficulty with meshing. Why not just use meshless finite elements? Right? Meshless finite element methods have the word meshless in the title, so they must solve all your problems with meshing. And the reality is that's not really true because meshless is a bit of a misnomer. Meshless finite element methods actually entails a process that in the end looks very, very similar to meshing. So for instance, I start out with my domain omega. I need to place some nodes in this environment to define my basis function, so I adaptively sample the geometry. And then something that's not always acknowledged when you talk about meshless finite elements is that in order to get convergence, the placement of these nodes has to satisfy some very stringent geometric criteria that are not so different from mesh quality criteria. So then you have to go ahead and optimize the placement of these nodes, right? You can't just put them wherever you like, and build a nearest neighbor graph that connects these nodes so that you can define basis functions. So the object that you end up with in the end is really not so different from a mesh. From there, the whole formulation is literally identical to all other finite element methods. You solve a big global system of equations, and in fact, you end up with matrices that are actually far more dense than with standard finite element methods. Okay? And just so that this is not just a kind of wild conjecture, we really did try out these meshless finite element methods on a large benchmark of about 10,000 models. And what we see is that when we try to solve some kind of variable coefficient problem on these PDEs, we get a behavior that is actually known in the meshless finite element world as stagnation. So these methods actually fail to converge. If we go and get kind of the latest and greatest research method for meshless finite elements, we see that things do actually now have some guarantee of convergence, but the error is wildly unpredictable. So across different models in the dataset, we have something like 100 million times variation in the error, right? So how much computation do you need to do to get good results? It's hard to predict. With standard mesh-based finite elements, things are a bit better, things converge, and the error is lower, but still quite unpredictable. And finally, when we do this with our Monte Carlo method, we get the best of all worlds, things converge, and we get very predictable error. Finally, when people hear about walk-on spheres, they often say, oh yeah, this kind of sounds like a boundary element method, right? You're talking a lot about the boundary and you don't need to mesh the interior, so this is just a boundary element method, right? And the answer is no. This is actually quite different because boundary element methods can't directly deal with things going on the interior of the domain, like source terms or variable coefficients. And to do this with a boundary element method, you actually have to do something like a hybrid of BEM and, guess what, a meshless finite element method for interior terms, right? So you run into all the same problems. Okay, so hopefully that gives a sense of kind of the overall challenges and trade-offs with different classes of methods. Okay, finally, let's take a look at some examples of things that you can do with a walk-on spheres solver. And when you go to implement these applications, it actually looks a lot like building a renderer. So if you have some experience with rendering, you know you have a scene that might have some materials and some lights and a camera that says which rays you want to shoot, and then the geometry where the critical operation is intersecting rays with the boundary of your scene. And then you use a Monte Carlo path tracer to estimate the illumination or the radiance in the scene. And people have thought very long and hard over the years about how to build good rendering systems, right? How do you make this efficient? How do you make the software well designed so that it's flexible and so on and so forth? Well, the good news is because we have all this parallel structure between Monte Carlo path tracing and walk-on spheres for PDEs, we can use a lot of the same wisdom to build a system for solving PDEs, except that instead of materials, we might have greens functions. Instead of lights, we might have boundary and source terms. Instead of a camera, we just have a description of where do we need to evaluate the solution. And instead of these ray intersection queries, we have kind of this critical part of the system, these closest point queries, which we talked a little bit about earlier on. And just as in rendering, the good news is closest point queries are easily computed for a wide variety of boundary representations. So we can work with polygon soup, meaning just a jumble of triangles that might have cracks or holes or whatever, right? There doesn't have to be any kind of special condition on the geometry. We can work directly with spline curves and surfaces, so sort of higher order representations. We can work directly with implicit surfaces, which are nice for blending or other kinds of modeling. We can work with instance geometry, so if we want to make many, many copies, maybe translated and rotated in different ways of the same model, that can be done very cheaply and easily. And just to stress how flexible this closest point idea is, we can even solve PDEs on domains with a fractal boundary. And kind of an important thing to say is we don't actually need to know the exact distance to the boundary. This all will work as long as we can compute a conservative bound on the distance to the boundary. Okay, so in terms of actual examples, here's one fun one. So let's say we want to take a vector field X and decompose it into its constituent parts, a curl-free part, a divergence-free part, and a remaining harmonic part, something called a Helmholtz decomposition. Well, we can do this by solving two Poisson equations using our standard Poisson estimator for two of those components, and then use our gradient estimator to subtract off those components and get the remaining harmonic part. The really cool thing that happens here is to actually draw these curves, to trace out these curves in the plane. We just need to run a standard ODE integrator using, again, our gradient estimator to decide which direction to move at each moment. And what that means is we never need to solve the PDE on the entire domain, only along the one-dimensional curves, or only along the sample points that we need for our ODE integrator, right? So this is a huge savings in cost, especially if we're now solving a 3D problem. Right? If we do 3D Helmholtz decomposition, we're only tracing out these curves and are doing a 1D subset of this three-dimensional domain. Here's an example that's kind of amazing that we can do without any meshes, which is we want to decompose a given domain, in this case given by Bezier curve, into nice coarse quadrilaterals, which then might be further subdivided for various kinds of modeling and simulation. So without going too much into the detail, we basically solve for a cross field by solving some kind of Laplace equation. We then use our gradient estimator to find where the singularities are, basically doing a gradient descent, and then again use the gradient estimator to determine what the index of each singularity in this field is, which we can then use to trace out these quadrilateral regions. And again, to stress, there's no mesh used at any stage of this process. We're solving this directly from Bezier curves. Now, why might that be useful? Well, there's a lot of well-known artifacts when you go to solve these kinds of problems with finite element methods. For instance, something that people sometimes call a singularity party, meaning just that there's aliasing in your solution of the crossfield if you're on a mesh, especially if you have very high degree singularities in this field that give a false sense of what's going on. This is something we don't have to worry about at all in the Monte Carlo setting. Okay, and then there's lots of other examples. For instance, we can do 2D shape deformation using our biharmonic estimator. We can compute diffusion curves. So this is a way of saying I'm going to solve a Laplace equation with two-sided boundary conditions to extend color from my curves into the rest of the domain. This is a kind of nice way of authoring vector graphics with nice smooth fills. We can do interactive editing, so we can explore the parameters of our model, the geometry, the coefficients, and so forth in real time. This is done in either GLSL or in Unity. And one thing to say too is these methods are often very easy to code. So within about 24 hours of putting our paper online, somebody had gone and taken one of our examples from the paper and recoded it from scratch in one of these shaders. We can also start to think about how to solve partial differential equations on curved surfaces. So far our domain has always been a flat subset of Rn, but let's imagine we have a conformally parameterized surface. Well, then the conformal scale factor that tells us kind of how the plane gets deformed into the surface can be reinterpreted as the coefficients for a variable coefficient differential equation. Right? And that lets us solve things like, again, diffusion curves on surfaces. In the future, we'd very much like to generalize this to arbitrary anisotropic parameterization so that we can solve PDEs directly on NURBS and subdivision surfaces and other patches that are important for modeling and engineering. Finally, we can give a little bit back to rendering by using walk-on spheres to help us with subsurface scattering. So depending on whether we're near the boundary or we're deep inside the medium, we switch back and forth between traditional volumetric path tracing and a walk-on spheres approximation of diffusion. So that gives just a little bit of a taste of what you can do with walk-on spheres, but of course there's much, much more that can be done with these algorithms. Okay. To conclude, I just want to mention a little bit of kind of recent work that's going on in this area, not just by us, but by other people. So there's been some work on kind of translating this idea of bidirectional path tracing, of starting not just from the observer, but from the emitter or from the lights into the setting of walk-on spheres, and that can help very much to reduce the noise, the error. There's been work on differentiable versions of walk-on spheres, some sort of preliminary work that says, maybe I want to find parameters of my PDE that explains things that I've observed. So this is something that's been very exciting recently in rendering and computer vision, using Monte Carlo renderers to try to understand which geometry produced an observed image, like this image of the chair. And likewise, in scientific or engineering problems, you might want to know, for instance, what was the density or what was the electrical conductivity or what were other parameters of your problem varying over space that produced some kind of physical measurement or observation. There's some very nice work on making exterior problems more efficient. So let's say I want to solve a PDE on the outside of a shape rather than inside. One thing I can do is let my random walks wander around, and if they get too far from the domain boundary, I just kill them off. But this is pretty slow and noisy. So a beautiful observation is that we can apply what's called a sphere inversion to turn this exterior problem into an interior problem if we also know how to transform the corresponding PDE. And that makes everything much more efficient. So here's just one example application from that paper of saying I want to apply forces to various molecules or atoms in a molecular dynamics simulation. And so for that, I need reliable estimates just at isolated points, just at kind of the locations of each atom. There's also been a lot of work on extending closest point queries to different kinds of geometry. So some very nice work on efficiently computing the distance to spline surfaces using sum of squares geometry processing, and also on finding closest points on neural implicit surfaces. So now you can use these closest point queries to directly solve partial differential equations on neural surfaces by running the walk-on spheres algorithm. There are also many very creative uses of PDEs in graphics and geometry processing, for instance, taking a curve and inflating it into a nice surface. We are currently working on generalizing and extending the walk-on spheres method from, for instance, not only Dirichlet boundary conditions, but also to Neumann boundary conditions, which in the past have really only kind of worked efficiently on domains that are convex. And so we very soon will be able to tell you how to do Neumann boundary conditions efficiently on arbitrary non-convex domains. And we're also thinking very hard about how to get some kind of global path reuse. So we've already done some path reuse locally with these tree walking strategies or next event strategies. But in rendering, there's been a lot of good thought on how to take paths globally and recombine them to get efficient estimators. And so we're doing something kind of akin to radiance caching or photon mapping in the walk-on spheres setting. Beyond these recent developments, there are, of course, many big questions still to answer. The biggest one being, which PDEs can we solve using walk-on spheres? Right? Because the more equations we can solve, the more applications we can have an impact on, where we can take extremely complex geometry and get kind of efficient, reliable solutions. We'd also like to think more about how do we share information between different estimators without losing some of the unique benefits of Monte Carlo, like parallelism. This whole enterprise is kind of by its nature stochastic. So if we have problems where the data itself, the measured data, has uncertainty in it, how do we incorporate that into our estimators so that we can kind of understand the uncertainty in the solution? How do we make this whole thing differentiable? There's been some preliminary work on that, but still a lot of questions to answer. Where are there high dimensional problems that benefit from walk-on spheres? So Monte Carlo famously kind of gets around the curse of dimensionality. We'd like to be able to take advantage of that for PDEs. And in general, for which applications does walk-on spheres offer unique capabilities? So I think the wrong thing to do is to just keep trying to solve the same problems that we've been solving with finite element methods, right? Those are actually very well adapted for the problems that they solve. Walk-on spheres does a lot of new and different things. So where can it really be beneficial? And here's a really nice example from Ryan Schmidt, where I'm trying to do some kind of agent path planning. So conceptually, this ball is going to follow a harmonic vector field that is extended from the boundary of the domain in order to follow this character that's running around. And in practice, I don't actually have to compute this vector field everywhere. I only need to know it at a single point at the center of this ball. So this is kind of an ideal candidate for walk-on spheres. I can run a ton of samples just from this ball center at very, very low cost. So these are the kinds of creative applications we'd like to see more of in geometric and visual and physical computing that really take advantage of walk-on spheres. And we would love it if you would join us on this journey of exploration. Okay, thank you very much.